rational exponents and radical functions. To begin dealing with this, we need to review the properties of rational exponents, properties of exponents, period. So just a real quick review. 0 exponent, any number raised to the power of 0 is 1. So for instance, if I had 3 to the 0, that would be 1. Okay, and we can go through the pattern on that, but since this is a review, I'm just going to state the rules here. Negative exponents, any integer raised to a negative power is equal to the reciprocal of the integer. So once again, let's stick with 3. If I had 3 to the, say, negative second power, that's going to be equal to 1 over 3 to the second. That negative essentially just means it moves to the other side of the fraction bar. Another example might be if you had 1 over 4 to the negative second. That would actually become 4 to the second power. Okay. Product powers property. When multiplying powers with the same base, add their exponents. So, for instance, if you had 3 to the second power times 3 to the fourth power, since the bases are both 3, you could say that's 3 to the 2 plus 4 power, or 3 to the 6th power. And then quotient properties, dealing with the same way. It's just if you have the same base, you subtract their exponents. So again, let's go ahead and use 3 to the second and 3 to the 4. That actually becomes 3 to the 2 minus 4, which is 3 to the negative second, which generally you'd write that using positive exponents. So we would write that as 1 over 3 to the second. Okay. Now let's go ahead and finish up the review here. We'll go 3, a power to a power, power of a power, when finding the power of the power, multiply the exponents. Say you have 3 to the second, all to the fourth. That would really mean you have 3 squared times 3 squared times 3 squared times 3 squared, which if we add those, we get 2 plus 2 plus 2 plus 2, or 3 to the 8. Well, the quick way is just say 3 to the 2 times 4. Okay. Powers of product property. Essentially, if you're finding the power of a product, find the power of each factor and then multiply. It's kind of almost like the distributive property. So if you think of it that way. So say you have 3a to the second power. You distribute that into each part. So you'd have 3 to the second times a to the second, which is 3a squared. Excuse me, that would be 9a squared. And then power quotient, same idea. It's just this time you're distributing to the numerator and the denominator. Okay, so you have, say, 3 over a all to the second power. That would give you 3 to the second over a to the second, or 9 over a squared. All right. Well, now that we went through those reviews, let's actually try to work through some of these. Quick reminder, when you're dealing with negatives and powers, if the negative is not included in parentheses, say like this first one, negative 2 to the fourth, it really means you have negative 1 times 2 to the fourth, or negative 1 times 2 times 2 times 2 times 2, which actually is negative 16. Versus negative, the quantity negative 2 to the fourth means negative 2 times negative 2 times negative 2. The negative is included to the power, which is equal to positive 16. So just a quick reminder there. Okay, so let's go ahead and use these. We have some rational exponents, so notice we're dealing with the same base with these fours, 4 to the fourth and 4 to the half. However, the fractions aren't the same when we're adding them, so we'd have to find a common denominator. Or we actually know 1/4 plus 1/2. Hopefully we know that's 3/4. Up with 4 to the 3/4 power. 5 to the 1/3 times 4 to the 1/2, all squared. Notice the bases are not the same. We have 5 and 4. So we're just going to bring this in and square each part. We get 5 to the 1/3. Oops, excuse me. 5 to the 1/3 times 2 times 4 to the 1/2 times 2. So the powers are both being multiplied by 2. That gives me 5 to the 2/3 times 4 to the 2 1/2 as a whole. 4 to the first, or 5 to the 2/3 times 4. And that's as far as we can go with that. Okay, another one here. Notice you have a negative exponent and you have parentheses. A couple ways you can do this. First thing I do, if I have a negative exponent and a set of parentheses, a quantity being raised to a negative, I just think of it as a fraction to begin with, and I move that whole piece down or to the other side of the fraction. So really it means now I have 1 over 5 to the second times 4 to the second, all to the positive 1/2 now because we've changed sides of the fraction. And so that means I have 5 squared to the 1/2, or 5 to the 2 times 1/2, times 4 squared to the 1/2, 4 times 2, or 4 to the second times the 1/2. So 2 times 1/2 is 1, so I have 5, and 4 times 2 to the 1/2 is, or 4 to the second to the 1/2, excuse me, is 4, which really means I have 20 as my denominator. So my answer is 1 over 20. The other way to do that at the beginning, you could have, right here, you could have thought of that as, if you wanted to, you could have thought of this piece as 5 times 4 squared, all to the 1/2 power. And then that would have just canceled out and you would have been left with 20. Multiple ways to do it. Okay, so this one here, I have 3 over 3 to the 2/3. And so really this is like having 3 to the first over 3 to the 2/3. So same base of 3. So I'm doing 3 to the 1 minus 2/3, or 3 to the 1/3. And then this guy right here, notice I have 56 to the 1/4 and 7 to the 1/4, and I'm squaring them both. Now I could either square it first, or I could do what I kind of did right here with the 5 times 4, and I brought it out because they're both being raised to the 1/4 power. So I'm going to do that. I'm going to have 56 over 7 to the 1/4 power. So really I kind of pulled out that power. And then all of that is going to be to the second power. So since the powers are the same, and really what that lets me do is it lets me reduce that fraction. 56/7 is just 8. So now I have 8 to the 1/4 power, all to the second power. 2/4 is 1/2, so this is really 8 to the 1/2 power. Really you're doing 1/4 times 2, right? So that's 8 to the 1/2. And that's really as far as I can go with it. All right, let's go ahead and move on here. Properties of radicals. So when finding the root of a product, find the root of each factor and then multiply. So once again, if I maybe go, say, I'm dealing with 3 times x and maybe the second root. What that really means is I'm doing the second root of 3 times the second root of x. Why don't we use something other than the second root, the square root? That seems silly. Let's say the 4th root. Okay, there's what I'm dealing with there. And so you're taking the individuals, and same thing with the quotient property. When finding the root of a quotient, find the root of each factor and then divide. So we could stick with the same stuff. So let's say 3 over x, and let's say we're taking the 4th root. So really that means the 4th root of 3 over the 4th root of x. Okay. All right, so let's try to apply those there. Using properties of radicals, simplify each expression. So this first one here, we have the 4th root of 2 times the 4th root of 128. Notice, just as I can separate the two, I can also put the two together. Since they're both the 4th root, I can put them both under the same 4th root symbol. That's 2 times 128, because they're the same root. Or the same, we're taking the same root of each. So that's really the fourth root of 256. So really, the only reason I do that is because 128 is not a perfect root, perfect fourth root, nor is 2. But when I put those two together, 256 is a perfect fourth root. Oops. It's actually, all right, come on, stay on that page. It's actually equal to 4. 4 times 4 times 4 times 4, 16 times 16 is 256. I'm kind of go the same route here. I'm dealing with cubed roots, so I can break that cubed root. Since 250 is not a perfect cube, nor is 2, I'm going to put those inside, and I'm going to do 250 divided by 2, which is going to give me the cubed root of 125, and that is a perfect cubed root. 5 times 5 times 5 makes 125. All right. Let's go ahead and try another one here. Now we're going to simplify some of these. So writing radicals in simplest form. So just in case we have forgotten dealing with radicals. Radicals with index n are in simplest form if no radicals with perfect nth roots. Nth powers as a factor other than 1. They don't have any perfect nth powers as a factor other than 1. No radicals contain fractions and no radicals are in the denominator. Okay, so really that just means is there a perfect root in terms of our index that goes into 162? So is there a cubed root that goes into 162, or is there a fraction inside that radical, or is this radical in the denominator? Okay. Well, I look at it, there's obviously no fraction in the radical, and there's no the radical's not in the denominator, but so I need to think of perfect cubes. Is there a perfect cube that goes into 162? So I think of like 2 times 2 times 2 is 8. Does 8 go into 162? Well, it doesn't. Does 3 times 3 times 3 or 27 go into 162? And when I start thinking of that, you may want to just start writing down perfect cubes, right? Like 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. So maybe off to the side of your paper, you're saying, okay, my x to the third power are these 27, and you're testing them as you go. And then maybe you use them on a different problem later, but I look at it and I know 27 goes into this. This becomes the cubed root of 27 times the cubed root of 6. 27 goes into 162 6 times. The cubed root of 27 is 1, 2, 3. And cubed root of 6, well, there's not a perfect cube that goes into 6, so I've now simplified it. And having these perfect cubes here actually helped me with the next one, right? I mean, I have the cubed root of negative 24. And remember, if it's an odd root, I can have a negative in here. If it's an even, I can't. But odd, I can. Okay, I know that. Well, 8 goes into 24. 24 is not a perfect cube because the next one's 27. But I know the cubed root of, and I'm going to make it negative 8. So anytime you have a negative, put the negative with the perfect cube times 3. 3 times 8 is 24, and they're both cubed roots, so cubed root of 8 is 2. Cubed root of negative 8 then is negative 2. And cubed root 3. All right. Well, looking at this one, I have a cubed root in the denominator. So what I need to do in order to get that out of the denominator is I need to make a perfect cube on the bottom. So what can I multiply 2 by to make a perfect cube? Well, once again, I look at my perfect cubes. 8. To multiply 2 by 4, I can make 8. So I'm going to multiply the cubed root of 2 times the cubed root of 4. And just so I'm not actually multiplying by a number other than 1, here's like a special number 1. Cubed root 4 times cubed root 4, or over cubed root 4 is 1. So I'm not changing the value, I'm just changing the structure here. So cubed root of 2 times cubed root of 4 is cubed root of 8. And cubed root of 7 times cubed root of 4 is cubed root of 28. The cubed root of 8 actually becomes 2. And that's the whole reason we multiplied by cubed root of 4. So we get the root of the denominator. So my solution is the cubed root of 28 over the cubed root of 2. Now you should always make sure that there's not a perfect cube that goes into 28, but there isn't, so we're done there. So we tried another one like that. Let me go ahead and switch colors here. So I have fifth roots now. I have fifth root of 4 and fifth root of 3. So I need to, since I have a radical in the denominator, I need to think, okay, what can I multiply the bottom by to find a number that is a fifth root? So I've got to think of like x to the fifth. Okay, well 1 times 1 times 1 times 1, right? 5. 5 times is 1. 2 times 2 is 4, times another 2 is 8, and 16 and 32. Okay, well, I know that 4 goes into 32, and it goes in there 8 times. So if I go the fifth root of 8, 4 times 8, that gives me the fifth root of 32 in the denominator. And that's what I want. I want a perfect fifth root. And so in order to make it so I'm not changing the value of the fraction, just the way it looks, I've got to multiply the top by the same thing so that this divided by this is 1. So in essence, I'm multiplying by 1. Fifth root of 8 times fifth root of 3 is the fifth root of 24. It is not a perfect fifth root. However, 32 is, that is actually 2. Right? 2 times itself 5 times makes 32. So this becomes the solution, fifth root of 24 over 2. Now I can't simplify that because I cannot simplify it because the 24 is in the root and 2 is not. So the different term there. All right. About conjugates, just a quick review. And we're kind of discussing that because it's going to allow us to get radical expressions out of the denominator. So in other words, where you're adding a radical to a number. So conjugate of a root, so a plus c root d. The conjugate, remember, is what you could multiply it by, and it'd actually get rid of that root completely, and that is a minus c root d. So really all you're doing is you're taking the opposite of that sign. The conjugate of a root b plus c root d is a root b, and c root d, exactly the same, it's just the middle is minus. The reason we have that, hopefully it'll make more sense when we see it right here. So if I want to get this radical out of the denominator, which is the problem right now, it's not in simplest form, I'd have to multiply by its conjugate. And when I do that, the conjugate of 6 plus root 3 is 6 minus root 3. Remember, I have to do it on both sides of the fraction bar, so in essence I'm multiplying by 1. It doesn't change the value. But notice when you multiply, I'll show it down here, 6 plus root 3 times 6 minus root 3, which is what you're doing on the bottom here. You're going this times this. That gives me 36 minus 6 root 3 plus 6 root 3. And so there's how you get rid of your radical. And then root 3 times negative root 3 is negative root 9. So notice this part is 0. I end up with 36, right, minus root 9, which is 3. Square root of 9 is 3, which is 33. So my denominator now becomes 33. My numerator is 1 times 6 minus root 3, or just 6 minus root 3. So I'm okay now. I have a whole number in the denominator, and I don't have any fractions under my radicand, and there's not a perfect square that goes into a 3. So I'm good to go. Okay, so let's go ahead and try this one here. I'm going to multiply by the conjugate. Conjugate is 3 plus root 5. So 3 plus root 5 over 3 plus root 5. That ends up giving me 3 plus root 5 on top. And 3 squared, 9. 5 squared, 25. Okay, so you'll notice I'm not even bothering multiplying out like this because the middle term cancels. So 6 squared was the 36, and root 3 times root 3 is root 9. So this is 3 times 3 is 9, and root 5 times root 5 is root 25. And I subtract in between, negative times positive. So I get 9 minus 5 on bottom, which is 4, and 3 plus root 5 on top. And I've got a radical out of the denominator. Okay, so let's go ahead and simplify like radicals. This is kind of a little easier. In order to add and subtract radicals, I have to have like terms or like radicals, and it means the root has to be the same as well as the base inside. So I'm counting fifth roots of 8. I have 2 fifth roots of 8 and 4 fifth roots of 8. So 2 plus 4, that means I have a grand total of 6 fifth roots of 8. I have 6 of them total. I can't take the fifth root of 8, so I can't simplify it, so I'm done. So looking at this, I've got 9 2 to the 1/4 powers and 5 that I'm taking away from. I have 5 of those 2 to the 1/4 power. So I'm dealing with the 2 to the 1/4. 9 minus 5 is 4. 4 times 2 to the 1/4. And here, well, root 48 and root 3, even though they're both fourth roots, they're not the same, so I can't just outwardly subtract those. But I could try to simplify. They're a perfect fourth power that goes into 48. So if I count by like x to the 4th, that would be 1, and then 2 times 2 is 4 times 2 is 8 times 2 is 16. Well, actually 16 goes into 48, so we can say that that's the fourth root of 16 times the fourth root of 3. And then minus, we bring down this fourth root of 3. That's good because fourth root of 16 is 2, 3 minus the fourth root of 3. So this is like having a 1 fourth root of 3. So 2 minus 1 is just 1 fourth root of 3. Alrighty. Okay, simplifying variable expressions. There's something we have to consider when we're simplifying. Roots of a value can result in both positive and negative numbers. So like the fourth root of 16 is actually equal to 2 and negative 2 because 2 times 2 times 2 times 2 is 16, and then negative 2 times negative 2 times negative 2 times negative 2 is 16. Pairs of negatives make positives. So when the root and the power are even and the same, you need to include absolute value to show that the number underneath the radical is a positive. We're not going to take the even root of a negative number. That's not a solution. In other words, like looking at this, since this index number and this power are the same, and they're both even, we have to say that the fourth root of x to the 4th is the absolute value of x. Therefore, you can't have a negative value inside that even root. Okay, so looking at that, it only affects those evens when they're the same. So this odd here is taking the cubed root of 24x cubed. Well, really, that's the cubed root of 24 and the cubed root of x cubed. So it doesn't affect odd powers. So when I look at this, well, the cubed root of 24, if I'm thinking of perfect cubes, I know that 8 goes into that. So we can break that down to the cubed root of 8. Sorry, that's supposed to be a cubed root there. So you got the cubed root of 8 times the cubed root of 3. And the cubed root of 8 is 2, so we got 2 cubed root 3. And then the cubed root of x cubed, so it's just cancel, and I'm left with just x. Okay, and so we have 2x, and then the cubed root of x, or the cubed root of 3, excuse me. Now, on this next one, notice I have fifth root, so once again, I'm not going to have to deal with this because it's an odd root. But I have the fifth root of 224. I have the fifth root of y to the 7th. The fifth root of 224, I could break that down to, if I think of perfect fifth roots, maybe you wrote down a table somewhere, but I know that's the fifth root of 32 times the fifth root of 7. And so once again, if you don't have a table written down somewhere, you're just listing, x to the 5th, like 1, and then 32, and then 4 times 4 times 4 times 4. You keep going. Or 3 times 3, I'm sorry. Times 3 times 3 times 3. Okay, but the fifth root of 32 is 2. So I have 2 fifth root of 7. And then when I'm simplifying this side, so I kind of treat it as like two different problems. I have that side and now this side. When you're dealing with a variable underneath, really all you're doing is you're trying to make that many, right? You're trying to make groups of 5. So when I think of the fifth root of y to the 7th, really I have y times y times y times y times y times y times y, 1, 2, 3, 4, 5, 6, 7. I think it wasn't like 32 of them or something. Okay, so I'm trying to make groups of 5 because my index is 5. Okay, so there is 5 of them. So the fifth root of y to the 5th cancels, and I'm now left with 2 left under there. So I'm left with the fifth root of y squared. Okay. The other way to think about it, if you think of exponents, you could say, okay, well, the fifth root of y to the 7th, that's the same as y to the 7/5 power. Okay, and the 7/5 power can be broken into y to the 5 over 5 times y to the 2 over 5, right? You can just kind of undo your powers here, and this is just 1, y to the 1st, okay, and y to the 2/5. So this y to the 1st right here is the one that, oops, I didn't write it down there, is the one that came out when we took the fifth root of y to the 5th. Okay, so we have that y to the 1st and then the y to the 2/5 right here. So it's really up to you how you want to do it. I think this is a decent visual. But when you're done here, your solution, you got to combine your pieces. So the things outside go first, 2y. The things inside go to inside the same root because they're both fifth roots, so 7 and y squared. All right. Next one, you're taking square roots. Well, square root 512 and the square root of x squared. Notice a square root means second root, and I'm only going to show that here because when I'm dealing with that, notice I have two evens. They're both even, and they're the same. So this is actually square root and squared cancel, but they're even and the same. That becomes the absolute value of x. So we've applied this principle up here now. And then the square root of 512, that's root 256 by root 2. And root 256 is 16, so we get 16 root 2 times root, or times absolute value of x. So if we put all those pieces together, it's 16 absolute value of x root 2. All right. Let's try a couple more just to make sure we're good. Okay, 405 to the fourth root of 405 x cubed y to the 8th. So we're going to go fourth root of 405, fourth root of x cubed, fourth root of y to the 8th. All right. Well, fourth root's 405, I think, like x to the 4th, right, is 1, 8, nope, 3 times 3 times 3 times, so 81. 81 goes into 405. It goes in 5 times. Okay. So that'll be the fourth root of 81 times fourth root of 5. Okay. And fourth root of 81 is 3. So we get 3 fourth root of 5. And then we'll treat this problem. Notice I can't make a pairing of 4 here because I don't have 4 x's being multiplied in there. So this part can't be simplified. This part just drops down. Fourth root of x cubed. I'm kind of at a dead end there. But this I can make 2 pairs of 4, right? I could break this down to having 2 sets of 4. So that's going to be if you think of it as like y to the 4th, times y to the 4th, or inside you could think of it as y to the 4th times y to the 4th squared. Okay, the 4's cancel, and I'm left with a y squared that came out there, right? Or better yet, maybe think of it as that power again, right? Y to the 8 fourths, which is y to the 2nd. Okay, and notice since I'm squaring this, I don't have to worry about my power here, this absolute value, because even if it was a negative, it's going to become positive because I'm squaring it. Okay, so this part becomes y squared. So on the outside, I have 3y squared, and then the 4th root of 5x cubed. All right, and we'll go one more here. So we have the 4th root. Let's go ahead and switch up some colors here. The 4th root of 128, the 4th root of x to the 7th, and the 4th root of y to the 7th. All right, 4th root of 128. Once again, looking at our 4th roots in terms of 128, we've got 2 times, you know what, this isn't 8. I just realized that. It's actually 16. Okay, so actually 16 goes into this. Okay, 4th root of 16. That was that 8 is the cubed root. And the 4th root of 16 times 8 makes 128. Okay. And 4th root of 16 is 2. And 4th root of 8, can't do anything with. So we're done there. Let's go on to this part of the problem. Think of this 3 problems. Break this down to the 4th root of x to the 4th times the 4th root, times 4th root of x to the 3rd, right? 4th roots cancel, but it's an even and they're the same, so that becomes absolute value of x. And 4th root of x cubed. So that's another way to show the work on these. Like over here, you could have broke it down like I did here. In fact, I'm going to do that on this one as well. So we'll go to 4th root of y to the 4th times the 4th root of y to the 3rd. These cancel. That's the absolute value of y since they are both even and the same. Times 4th root of y cubed. And so on the outside, I have 2 absolute value x, absolute value y, and 4th root of 8 x cubed y cubed. All right. Well, we're almost there. There's a lot in this lesson. This textbook includes tons in this lesson. So I got a couple problems left. So writing variable expressions in simplest form. So same idea. It's just you have more variables in there. So let's go ahead and take this the cubed root of 2. So cubed root of 2 and the cubed root of a to the 14th and cubed root of b to the 7th and cubed root of c to the 9th, right? And so I'm looking at a cubed root of 2 I can't do anything with, so I'm kind of at a dead end there, so I'm just going to circle it. Cubed root of a to the 14th, I could think of that as 3 goes into 12, so I could say, well, that would be like the cubed root of a to the 12th times the cubed root of a squared. And I know that I can get 4 a's out of that, so a to the 4th and cubed root a squared. So I'm kind of done, dead end there now. And then cubed root, I know 3 goes into 6, so b to the 6 and cubed root b. Okay, so this part goes in there twice, so that's b squared, cubed root b. And then that's actually perfect cube. 3 goes into 9 3 times, so that's actually c to the 3rd. So I've got a dead end on each of those. So underneath or outside my radical, I got a to the 4th, I got b to the 2nd, I got c to the 3rd. And then I have the cubed root of 2 and a squared and b. Holy moly. This one I have a radical in the denominator. Can't have that, so I want to get it out there. So I need to think, just like I did over here, in terms of what number will 3 go into that's close to 7. Goes into 9. So if I multiply this by the cubed root of b to the second, that's going to give me the 2 more I need to get to 9. And do the same on top. So in essence, I'm multiplying by that 1 again. So that's the cubed root of b to the 7th and b squared. So that really gives me the cubed root of b to the 9th. And a squared times cubed root. I'll make that look more like a cubed root there. B squared. And so cubed root of b to the 9th, that becomes b cubed. And so now I end up with a squared cubed root b squared over b cubed. All right. And the last one on this page here, kind of a doozy. So I look at it as 3 different problems, or well, really 4 different problems. I'm going to match up the numbers. So I'm going to think of this as 16 over 8. That's one problem. A squared over a to the 4/3. That's another problem. B to the 2/3 over b squared. And then like a 1 over c to the negative 5th. So 4 problems. 16 over 8 is pretty easy. That's 2. A squared minus 4/3. And b to the 2/3 minus 2. And then this negative has to come up, so it's just c to the 5th. And so now I have 2. And 2 minus 4/3 is 2/3. So a to the 2/3. 2/3 minus 2 is negative, negative 4/3 there. That's b to the negative 4/3. And then c to the 5th. That means my solution, if I think of that over 1, this piece is just going to move down. I'm going to have 2a to the 2/3, c to the 5th, over b to the 4/3. Makes it a little less intimidating if you have 4 different problems there. All right, one last piece, and this first part looks pretty easy because I'm dealing with the same base. So I'm just counting root a's. 4 root a plus 7 root a. That's the grand total of how many root a's? That's 11 root a's. All right, and we're going to assume all variables are positive. We don't have to deal with any plus and minus or absolute value stuff there. So this last one, I'm taking cubed roots, but I'm not taking the cubed root of the same thing, so I can't just subtract. I can do the 5 and cubed root of 4, and I can break apart the cubed root of x to the 8th. And then I'm going to break apart everything inside the radical on the other one. So I'm going to have the cubed root of 32 and the cubed root of x to the 5th. And cubed root of x to the 8 is actually the cubed root of x cubed, x to the 6th times cubed root of x squared, and then 5 cubed root 4. Okay, so this part broke into those. I took the x to the 6th because 3 goes into it twice, so that whole thing becomes x squared. I have cubed root x squared there, and then the cubed root of 4 and 5 there. Okay, can't do any more with those, so this side all becomes 5x squared cubed root 4x squared minus, and so if I come over here now, just think of it like that. Cubed root of 32 is cubed root of 8 by cubed root of 4. Those two become that, and this would become cubed root of x cubed and cubed root of x squared. And so cubed root of 8 is 2, cubed root 4, and cubed root of x cubed is just x, and cubed root of x squared. So I'm left with 2x cubed root 4x squared. Convenient, since now we have a cubed root of 4x squared, cubed root of 4x squared, I have 5x squared, and this over here is 5x. And this over here, yep, got. Oh, you know what? I forgot to bring this 4x down, so we better drop that down there. So we have that 4x we have to deal with as well. So I forgot that all the way down there. So 4 times 2, this should actually have been 8x squared. So we have 4 times 2 times x times 8x squared. And x cubed, yep. So now we have 5x squared minus 8x squared is negative 3x squared. And we're counting the cubed root of 4x squared. So yeah, don't forget to bring down the extra piece down. I should have done that immediately there. There, we've got it. All right, I think that's all I got there. Good luck, you.